Hello everyone, welcome back to my channel. In this video, I'll tell you how to implement binary to gray and gray to binary code converter using gates as well as using MSI ICs like decoder IC. This topic is very important for digital electronics, and also this is basic topic in digital electronics. So first you should understand what binary code is and what gray code is. So binary code is also called as base 2 code. It means it has only two symbols, 0 and 1. Similarly, gray code is also base 2 code. It also has zeros and ones. But gray code is also called as reflected binary code. It means two consecutive numbers differ by only one bit. It means if I'll write 2-bit binary number, how I'll write? I'll write it at 00, 01, 10 and 11. Here you can see both bits are different. Here bit LSB was 1, here it is 0. Here MSB was 0, here it is 1. So in such code, probability of error occurrence is more, and that is why gray codes are used. In gray code, numbers are 00, 01, 11 and then 10. So here you can see LSB is same and MSB is changed. So in this video, I'm going to tell you implementation using both methods. So this video is basically divided into two parts. One is part A is about implementation using gates, in which you'll come to know from where these equations came. And second part is implementation using decoder IC. So in examination, question can be like implement binary to gray or gray to binary code converter using gates. Then you can use part A. And for MSI IC, you can implement using part B. Initially, I thought of making two different videos, but then I thought if I'll make single video, then understanding of the topic will be in a better way. Applications of gray code are in rotary encoders, in flash ADCs and in K-maps. So let's start with binary to gray code converter, and then we will see gray to binary. So here I have taken example of 3-bit binary to gray code conversion. So 3 binary bits are B2, B1 and B0, and we all know how we write binary number. It is 1, then 2 and then it is 4. So here I'll write 4 times zeros and then 4 times 1. 2 is 2 times zeros, 2 times 1, 2 times zeros, 2 times 1, 0, 1, 0, 1, 0, 1, 0, 1. And why it is 1? 2 raised to 0 is 1. 2 raised to 1 is 2. 2 raised to 2 is 4. It is base 2 number. So base is 2 and then 2 raised to 0, 2 raised to 1, 2 raised to 2, then here 2 raised to 3. So here if 4th bit is present, it is 8 times zeros and then 8 times 1. So this is my binary number. Now let's find the equivalent gray number. So see, as per these equations, you will come to know from where these equations came. First, we'll complete this table and then you'll understand. G2 is equals to B2. So B2 is 4 times zeros, 4 times 1. So G2 and B2 are same. G1 is B2 XOR B1. B2 XOR B1. So 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 0 1 1. 1 0 1 1 0 1 1 1 is 0 1 1 is again 0. Truth table of XOR gate is when both inputs are same, 0 0 or 1 1, then output is 0, else output is 1. Then G0 is B1 XOR B0. B1 XOR B0. So 0 0 0 0 1 1 1 0 is 1 1 1 is 0, again 0 0 is 0 0 1 is 1, 1 0 is 1 and 1 1 is 0. Now see why it is called as reflected binary code, because you can see here it is 0 0 1 1 and then if I'll put line here or mirror here, then it is exactly opposite, 1 1 0 0. Similarly 0 1 1 0, and if I'll put mirror here, it is 0 then 1 1 and then 0. Now let's find out equation for G2 by using K-map. Here we have 3 outputs, G2, G1 and G0, and that's why we need 3 K-maps. And number of inputs are 3, that is why 2 raised to 3 is equals to 8. So 8 cell K-map we will use here. So let's put values for G2. It is 4 times zeros and then 4 times 1. So 0, 0, 0, 0, 1, 1, 1 and 1. See, here we use gray code. So it is 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 1 is 3, 0, 1, 0 is 2. So in K-map numbers we put like 0, 1, 2, 3, 4, 5, 6 and then 7. So here let's group them. So what we can do? I'll make one chord. And for this chord, equation is B2. B2 is 1, so B2. So G2 is equals to B2. Then for G1, 0, 0, 1, 1. Again 1, 1, 0, 0. 1, 1, 0, 0. So what I can do? I can make two pairs. This is my first pair. This is my second pair. So equation for this first pair is value of B2 is 0. So B2 bar, and here what is common? B1. B1 is 1. B1 plus for this pair equation is B2, and here what is common? B1, and value of B1 is 0. So B1 bar. So you can see this is B2 bar B1 plus B2 B1 bar, like A bar B plus AB bar, which is equation of XOR gate. So here B1 XOR B2. Now let's find out equation for G0. So here values are 0, 1, 1, 0, 0, 1, 1, 0, and then again 0, 1, 1, 0, 0, 1, 1, 0. So here what we can do? We can make two pairs again. One pair and this is another pair. What is the equation here? B1 is 0. So B1 bar and B0 as it is, plus here B1 B0 bar. See, when we make K-map, the separate video I have uploaded, the link is given in the description box. What we will have to do? We need to compare the rows and columns. So here you can see nothing is common. Value is 0 and 1. So we can take anything here. Here we don't have anything to compare. So we will have to take both variables. And if value is 0, we take bar of that variable. If value is 1, we take variable as it is. So here again it is like A bar B plus AB bar. That is XOR gate. So B0 XOR B1. From these K-maps, these equations came. Now let's implement these equations. Let's take B2, B1 and B0, three inputs. What is G2? G2 is equals to B2. So here G2 is equals to B2. What is G1? B1 XOR B2. So I'll have to use one XOR gate. And here I'll get G1. But what is input? B1 and B2. So one input is B2. Another input is B1. So G1 is B2 XOR B1. What about G0? G0 is B0 XOR B1. So again I'll have to take one XOR gate. Output of that XOR gate is G0 and inputs are B0 and another input is B1. This dot indicates connection. So this is my binary to gray code converter using gates. In part 2, we will see how to implement binary to gray code converter using decoder. Now first, let's complete gray to binary using gates. So 3-bit gray to binary. So I'll write gray code first. Here it is 4 times zeros, 4 times 1. Then comes 0, 0, 2 times zeros, 2 times 1, 0, 0, 1, 1. And there at the mid, we will put mirror so that the remaining part is reflection. So here 1, then this 1 and then 0 and then 0. Then here the upper part is same as binary code. 0, 1 and then I'll have to put mirror here also. Then 1, 0, 0, 1, 1, 0 because there was only 1 bit change. So I need to put mirror after 2 bits. Now I'll write binary equivalent of this. So binary numbers are simple. 4 times zeros, 4 times 1, 2 times zeros, 2 times 1, 0, 0, 1, 1. And then comes 0, 1, 0, 1, 0, 1, 0, 1. Before we make K-maps, let's write the decimal equivalents. Decimal equivalents are 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 1 is what? 3, 0, 1, 0 is 2, 1, 1, 0 is 6, this is 7, 1, 0, 1 is 5 and 1, 0, 0 is 4. Or you can see here, how do we write binary code 1, 2 and then 4. So 4 plus 1 is 5. Here 4 plus 2 is 6. Okay, so we have decimal numbers, we have gray numbers and we have binary numbers. Now let's make 3 K-maps for these 3, B2, B1 and B0. These 3 are K-maps. This is for B2. So let's put values of B2. B2 is, see this is like 0, 1, 2 and 3. So 0, we need to know decimal numbers now. We need to check decimal numbers now. For 0 it is 0. So I'll write 0. For 1, 0. For 3, 0. For 2, 0. For 4, 5, 6 and 7 it is 1. So 4, 5, 6 and 7 it is 1. So what I can do? I can make one chord and here nothing is common. Here it is G2. So B2 is equals to G2. Now for B1 it is, for 0 it is 0. For 1 it is 0. For 3 it is 1. For 2 it is 1. For 6 it is 0. For 6 it is 0. So see 0, 1, 2, 3, 4, 5, 6 and 7. So for 6 it is 0. For 7, 0. For 4 and 5, 1, 1. 1, 1. So what I'll have to do? I'll have to make 2 pairs. And then I can write equation as, for this pair it is G2 bar and here G1 plus for this it is G2 and G1 bar. So this equation will become G1 XOR with G2. Equation for B1. Then for B0. So let's put values for B0. For 0 it is 0. For 1, 1. For 3, 0. For 2, 1. Then for 4 it is 1. For 5 it is 0. For 6 it is 0. And for 7 it is 1. So we don't have anything to make pair or chord. So what we'll have to do is, we'll have to make separate groups. And let's write an equation. So for B0 it is, for this G2 bar, G1 bar, G0 plus for this G2 bar, G1, G0 bar plus for this G2, G1 bar, G0 bar. Here both are zeros. Plus for this G2, G1, G0. Let's minimize it. So here, if I'll take G2 bar common, then in bracket it is G1 bar, G0 plus here G1, G0 bar. G1, G0 bar. Plus, if I'll take G2 common here, then in bracket G1 bar, G0 bar plus G1, G0. So this is, see, G2 bar in bracket, this is G1 bar, G0 plus G1, G0 bar. This is nothing but G0 XOR G1 plus this G2 and this is what? A bar, B bar plus AB, that is XOR gate. So G0 XOR with G1. It means bar of XOR. So this is like A bar, and if this whole bracket I'll consider as B, A bar B plus A B bar. So this is nothing but G0 XOR G1 XOR G2. And you can see here G1 XOR G2 is nothing but B1. So this is G0 XOR B1 by putting this value of B1. Now let's implement the circuit. So what we have three inputs, G2, G1 and G0. You can see B2 and G2 are same. So here I'll get B2. For B1, it is G1 XOR G2. So I need again XOR gate. Here I'll get B1. Inputs are G1 and G2. So one input is G1, another input is G2. Here it is G0 XOR with B1. So I'll take one XOR gate which will generate B0 and inputs are G0 and another input is B1. So this B1 I'll take here. In this way I can implement gray to binary code converter using gates. Now let's start with part 2. Binary to gray using decoder. So in decoder there are two types where outputs are active low and in few decoders outputs are active high. So in few books you may find that outputs are connected to OR gates and in few books it is given as they are connected to NAND gates. So don't get confused. It is because of outputs of decoder. They are either active low or active high. So here I am going to use IC138 because in many times for practical implementation, for practical exam, this is given as a title. So IC74138 is 3:8 decoder. It has 3 inputs and 8 outputs. All outputs are active low outputs. Meaning is the selected, this is decoder. It means if its value is 0, 0, 0, if selection input is 0, 0, 0, it will select first output and it will make first output 0 and remaining outputs will remain 1. If select input is 1, 1, 1, that is 7, then it will select Y7, it will make Y7 0 and other outputs will remain 1 because outputs are active low. In case of active high, selected output will become 1 and remaining outputs will remain 0. That is basic difference between active low outputs and active high outputs. So here I have chosen IC74138 which is with active low because in many universities I have checked the syllabus and it is, this topic is used for practical implementation so that it will be easy for you to implement. So this is, if in exam only part 2 is asked, then you can describe what decoder is, which has select inputs and which has outputs. Then it has 3 enables. Enable E1 is active high. So we need to connect it to VCC. E2 bar and E3 bar. Bars are given. Whenever bar is given, it means it is active low. So we need to connect them to 0. Then only they will act. Enable pins are like, if you wanted to turn it on, you will have to enable it. For that it is used. Here HC indicates high speed CMOS and here LS indicates low power Schottky transistors. So this is CMOS IC, this is TTL IC. But their functionality is exactly same. Now let's see how to implement binary to gray code. This is my 3-bit binary code. Now let's write gray equivalent of it. So you have this table. I'll write it again. So this is my gray code. For implementation using decoder, we need to write equations for G2, G1 and G0. So G2 is summation of M. We need to identify the min terms for where output is 1. So here output is 1. For 4, 1, 0, 0 is 4. For 5, for 6 and for 7 output is 1. For G1 it is 2, 3, 4, 5. Summation of M 2, 3, 4 and 5. For G0 it is 1, 2, 1, 2, 1, 0, 1 is 5 and 1, 1, 0 is 6, 5 and 6. This is our decoder which has 3 inputs S0, S1, S2. S0 is my least significant bit. So I'll connect my least significant bit B0 to S0 and B2 to S2. Enables E1 is connected to VCC, E2 bar and E3 bar are connected to ground because they are active low. Now these are my outputs. How many outputs I have in gray code? I have G2, G1 and G0. Our decoder will generate active low outputs. So we need to invert them. What we want is 1. We have taken min terms. So we need to use NAND gates. And how many inputs are there? 4 inputs are there. So I'll use 4 input NAND gates. 1, 2 and 3 gates. And their inputs are 4. So these are my 3 NAND gates for G0, G1, G2. For G0, the inputs are 1, 2, 5 and 6. So here I'll take 1, 2, 5, and then next is 6. And here I'll get G0. For G1, 2, 3, 4, 5. So 2, 3, 4 and this is my 5. 2, 3, 4, 5. It should not go inside gate. And here for G2, 4, 5, 6, 7. 7, 6, 5 and this is my 4. So in this way, if you will implement your circuit, you will get G0, G1 and G2. So this is again our LSB. So if you have 3 LEDs like this on your board, you will have to connect G0 here, G1 here and G2 here. And this is MSB. So in this way, you can implement binary to gray code converter using decoder. So in exam, if question is to implement binary to gray code converter using MSI IC, then this much part is sufficient. No need to write all those XOR implementations, K-map. You just need to write this truth table for binary, for gray. Then you need to explain what 74138 decoder is. It has active low outputs and that is why NAND gates are used. In case of active high outputs, instead of NAND, you can use OR gates. Now let's see gray to binary code. So let's write gray code first. So these are gray codes. These are equivalent binary codes. I have already implemented it. So I have already explained how binary codes came from gray codes and how these equations came. Let's write the decimal equivalents because we need to identify min terms. So here 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 1 is 3, 0, 1, 0 is 2, 1, 1, 0 is 6 and so on. So let's write equations for B2. It is summation of M 4, 5, 6 and 7. 4, 5, 6 and 7. For B1, it is summation of M. I am taking min terms. It means terms for which my output is 1. So here output is 1 for 3, for 2. So 2, 3 and 4 and 5. 4, 5. For B0, for 1, then for 2, then for 7 and 4. 4 and 7. Then in same fashion, we'll draw decoder first. So this is my 3:8 decoder with active low outputs. So I have used 74138 simply. Y2 bar, Y3 bar, Y4 bar. Bar indicates active low. It means output is 0. Y7 bar. Now I need to take again 3 NAND gates because I have 3 outputs B2, B1 and B0 and for every output there are 4 inputs. So I'll have to take 4 input NAND gates. So I'll draw 3 NAND gates. What are inputs for B0? 1, 2, 4 and 7. So first input is 1, then 2, then 4, and next is 7. One, 2, 4 and 7. For B1, there are 2, 3, 4, 5. 2, 3, 4 and 5. This is 4 and then next is 5. 2, 3, 4, 5. For B2, there are 4, 5, 6, 7. So this is 4. This is my 4. 4, 5, 6, 7. This is 5. Then 6. And this is my 7. So if you will implement this circuitry, here you will be able to convert your gray code into binary code. It means if you will apply gray number, let's say 110, 1, 1 and 0. For 110, this 110 means 6. Sorry, this is my LSB. So G0 is 1, G1 is 1 and G2 is 0. So this is not 6, this is 3. So for this 0, 1, 1, remember G2 is MSB. For 0, 1, 1, it will select Y3. So what it will do? It will make Y2, Y3, 0 and all other outputs will become 1. So this Y3 is connected to B1. For this, see, Y3 is only connected to B1. So in case of NAND gate, any one input is 0, then output is 1. So this B1 will become 1. For this 0, it will generate 1. For other NAND gates, other two NAND gates, all inputs are 1. So it is exactly opposite to AND. When all inputs are 1, in AND gate, output is 1. So here in NAND gate, it will become 0 and 0. So it is 0, 1, 0. So you can see here 0, 1, 0. In this way, you can verify your circuit. In similar fashion, you can also verify binary to gray also by putting numbers here. You need to remember which is LSB and which is MSB. Here B2 is MSB, B0 is LSB. I hope this video will be useful to you for theory as well as for practical implementation, and it will clear your understanding of binary to gray and gray to binary. Don't get confused. Question can be to implement using gates, and if it is using MSI ICs, then you will have to use this method. Else you will have to implement using simple XOR gates. So thank you so much for watching. Don't forget to like, share and subscribe to my channel. Thank you, and also check out other videos on my channel. Thank you.